Let's move on to the third section of this lesson. This one is about calculating the absolute maximum minimum and also doing something similar to that, intervals of increase decrease, and finding out the nature of the critical points problems when the algebraic expression of the function is given. Easy of the two is absolute extrema, so let's talk about those. How do I find out absolute extrema? Usually graphic aid is the starting point. You must have your calculator or any graphic aid, so use it. Graph it, and then here in this picture I drew a little bit better picture using this Mathematica, but you can actually draw it from -1 to 1, and you can anticipate where the absolute maximum and absolute minimum are, the highest value and the lowest value, here and there. Of course, these values are a little bit unclear, but if you see a graph and you have concrete idea in advance, then you can do the problem a lot easier from that point on. The candidates are, of course, the endpoints. So -1 and 1 are obvious candidates, and then we have another point where the derivative becomes 0. So automatically plug in x equals to -1 starting point and x equals to 1, find out. Turned out to be they are both 1, and then we have to find out third, maybe a little bit more points by taking the derivative and setting it equal to 0. This was rather easy computation because this turned out to be a quadratic equation. And then we get 1/3, so plug it in. The biggest is absolute maximum, the smallest is absolute minimum. If you have a little bit more complicated function, again you can use the same strategy. How about something like this? X equals to 0, x equals to 2. Those two are obvious candidates because we can have you can have absolute maximum or minimum in the endpoints. And then of course you have one or more points from taking the derivative and setting it equal to 0. And here's a way to solve a transcendental equation. Take the derivative and set it equal to 0, factor it, and then you end up with a 1 factor equal to 0 because exponential is never 0. And it turned out we have a solution, and then plug in that solution, that critical number, and endpoints. And the biggest is the global maximum, and the smallest is its global minimum. Of course, that's a little bit old-fashioned way. This is a little bit better. Just plot the graph, and then I draw a little bit better picture using this dotted line and so on. But you can just draw it from 0 to 2, and you're going to anticipate, look, global minimum here at x equal to 0. And then this is not going to be it, and we expect one more around here. And then go ahead with taking the derivative and setting it equal to 0. You can do this problem a lot better. So we have technology available, so use it. Coming back to this derivative and setting it equal to 0, don't be intimidated by these transcendental terms because exponential functions exponential terms will turn out to be easy, because even if you take the derivative, they will stay the same, so they're going to end up with a common factor, and you can always factor it out. And then exponential is never 0, so you're going to get a smaller equation. What about local maximum minimum type of problems where you have to find out intervals of increase and decrease? Those are going to be harder because if you determine all the local extrema, and then absolute extrema must be, well, biggest of this local maximum and smallest of the local minimum and so on. So if you can do local maxima, then absolute maxima and minima are actually easier. For that reason, I have never written absolute maximum minimum problem, I think. Have I? I don't know. I just don't think this is really important problem for exam preparation because there are more important and also more difficult problems available, kind of like these. Let's begin with easier problem. This one is a bit too trivial, and actually we already saw it before. So let's move on to this one. So how do we handle it? Well, okay. Let's cheat a little bit. Using your handheld calculator, you can get a graph, and the graph will show you something like this. In the graph, you can anticipate local minimum at x equal to 0, and then neither maximum nor minimum at x equals to 1. But of course, that's what you get from calculator, so you need justification. However, if you have a concrete idea in advance, it'll make the problem that much easier. Now, how do we handle these problems? You have to find out the critical points first. So let's take the derivative. Okay, did I get the derivative correctly? Okay, now that I got the derivative, I'll set this one equal to 0. Equal to 0, and then I can factor 12x out, and then what do you get? X squared minus 2x plus 1 is gonna remain, and that's gonna be a complete square. X minus 1 squared equals to 0. So what do I get? I have x equal to 0 and x equals to 1. Those are the critical numbers. X equal to 0. Those are critical numbers. Now we have these two numbers, and then we have the graph. So the nature of the critical points are actually local minimum and the neither maximum nor minimum. Pretty clear from this picture, so you can answer all the questions. Decreasing from negative infinity to 0, increasing from 0 to 1, increasing again from 1 to infinity. This is local minimum at x equal to 0, and then neither maximum nor minimum at x equals to 1. At x equal to 0, we're going to get absolute minimum as well. Of course, if you do not have that picture with you, without this technology aid, it's going to be far more difficult. But nowadays, calculators are part of the strategy, so we can do that. By the way, in this particular problem, it was rather clear this was 0, this was 1, so that kind of computation was maybe not necessary, but very frequently you can see local minimum, you can see these critical points, but what x values, just by looking at the graph, they may be a little bit unclear. In that case, taking the derivative and setting it equal to 0 to actually finding out is actually important. Another thing, I didn't ask you to find out the inflection point in this problem, but I could. In that case, what do you do? I expect an inflection point around here, but it's hard to see from this picture. Well, inflection points occur when you have local maximum or local minimum of the derivative function. Consequently, when the second derivative becomes 0. Therefore, you can take the second derivative and then set it equal to 0 to find out the inflection points. So that's 36x squared minus 48x plus 12, and set it equal to 0, and what do I get? I have not getting 12 out, I have 3x squared minus 4x plus 1 equal to 0. So I'm gonna get 12, 3x minus 1 x minus 1 equal to 0. Alright, I have it. X equals 1/3, x equals to 1, and those two are going to be the inflection points. X equals to 1 right here, that's an inflection point. That's pretty clear because this is neither maximum nor minimum, so it's an inflection point. The other inflection point is a little bit unclear, but it is around here at x equals 1/3. We can find out all these. I'm going to leave the students to fill out the rest. Okay, let's move on to another kind of problem, a little bit more challenging. How about this one? Again, to save some time, let's just look at the picture and then let's just minimize this part so that I can see the problem and the graph in the same viewing window. And I expect a local minimum around here and local maximum around there, but their positions are a little bit unclear. Here I use mathematical command to calculate symbolically, so I know critical numbers are 1 over square root of 2 and negative 1 over square root of 2. But with your handheld calculator, it's difficult to find out. You'll have to do something like this. H prime of x, use product rule to calculate. Derivative of first function is 1 e to the negative x squared plus first function times derivative of second function times derivative of the inside. That's my derivative function. So simplifying this, we get e to the negative x squared function minus 2x squared times e to the negative x squared. Setting this one equal to 0, actually before setting that equal to 0, I can factor this exponential. I did that because I'm going to set this one equal to 0, and if you set something equal to 0 and solve it, factorization is usually the key, so I did that. Now, exponential is never 0, so this one has to be 0, so we get a smaller equation. And this is an easy equation to solve. X squared is going to be 1/2, so x is plus or minus square root of 1/2, and those are the critical numbers. And of course, Mathematica found the same thing too. Now that we found out this one and that one, we know their nature, and then you can say x has local maximum at x equals to square root of 1/2, local minimum at x equals to negative square root of 1/2. By plugging these values and calculating, you can find out the y-coordinate of those critical numbers too. And then intervals of increase or decrease, decreasing from negative infinity to negative square root of negative square root of 1/2. From negative square root of 1/2 to positive square root of 1/2, increasing, and then decreasing from that point on. Everything can be answered.